Okay, so a few questions on instrumentation systems. Okay, so something where we've got a circuit like this where we've got two sensors connected together is a bridge circuit. Okay, a few problems with the pen there, but let's see how we go on. Okay, so we need to work out what the voltage is at P and the voltage at Q are. Well, as we've got a 2K resistor and a 2K resistor there as a potential divider, 12 volts across it, they're going to split the voltage evenly each. So therefore, the voltage at P is just going to be 6 volts. I'm not going to work that out. The voltage at Q then, we've got we're told that we've got the resistance of the thermistor is 1.75 and the resistance of the variable resistor, which is at the bottom there. So that's where we're looking if we're measuring the voltage at Q. First of all, across that resistor. So we've got 2K over 1.75K plus 2K times by our 12 volts gives us 6.4 volts. Okay, so looking at that there, we've got 6.4 volts there, we've got 6 volts there. Okay, so therefore V out is going to be the difference between the two, so 6.4 minus 6 equals 0.4 of a volt. Okay, if we scroll on and then look at a slightly different balanced bridge and look at the components that we've got, when this bridge is balanced, what we want to happen is for the same voltage to be out on A and the same voltage to be out on B, so that the difference between the two terminals is 0. So therefore, we've got the voltage across our variable resistor, and we're told that the strain gauge is 120 ohms, and we've got 100 ohms over 100 ohms. Now, it's a very straightforward. If that ratio of that two resistors must be the same ratio as that two resistors, but I've just put it in that way so you can see it in case it wasn't as easy to see. But you can see that our variable resistor is going to be 120 ohms, so that we've got the same voltage on A and the same voltage on B. Okay. So, as it stands at the moment, if they've got the same voltage across them, then the voltage at B and the voltage at A must be the same voltage, therefore they must be 6 volts each. Okay, so we need to know this, so that now the output voltage has changed, because under stress the bridge circuit outputs at minus 50 volts. So there's our strain gauge. Okay, there's our strain gauge, the ones that's actually doing the measuring. So the voltage at B hasn't changed. B is still equal to 6 volts in terms of terminals. And the voltage at A, okay, so we've got minus 50 millivolts, which means that the voltage at A must be 6.05 of a volt. Why is that so? Well, okay, if I take the voltage, if I got 6 volts here at the top minus 6.05, I end up there with minus 50 millivolts. So that's why that's true. So then looking at what we're looking to work out, we're looking to work out, we know what the value of this, we just want to know what the strain gauge value is read. So looking at it in terms of a picture, we've got our strain gauge there, and we've got 120 ohms there, and we've got 6.05 of a volt there. So therefore we can work out the current going through this 120 ohm resistor. We've got 12 volts there. So the voltage across that 120 ohm resistor, so current is equal to voltage divided by resistance. So the voltage across that resistor is going to be 12 minus the 6.05 of a volt, and divided by the 120 ohms that it is. So we get a current of 49.58 milliamps. That same current then is going through this strain gauge. So the resistance of the strain gauge is voltage divided by current. We know that there's 6.05 volts there, so that's what the voltage is across it, divided by the 49.58 milliamps going through it, gives us a resistance of 122 ohms. Okay. Right. Okay, so now we're looking to draw ourselves a difference amp, and we need to define some components. So a difference amp is based on an inverting amplifier to start with. So I'll do the inverting amplifier bit like so. We've got RF and RIN. Well, a difference amplifier needs two input terminals, so I'm going to repeat my RIN there like so. That's not a great drawing, is it? Let's draw my RIN again. Like so. So that's RIN, and then I need an RF there that goes down to 0 volts. Okay. So with any amplifier, gain is equal to V out divided by V in. So we've got 10 volts out. We've got 10 volts out when we've got 20 millivolts going in. Okay, so therefore that's a gain is equal to 500. Okay, so therefore choosing any values of components, 500k, 1k, and 500k, 1k. So two RF values are the same value, the values of 1k are the same value. So that's that part of the circuit. Now we need to move on to the sensing. So we're looking at encoding discs, so we can look at measuring position. So the outer ring is the least significant bit, so there is the least significant bit on A. Well, it asks us for B, so we've got a 1 there to start with, and a 0 and a 0. 1, 0, 0 on B. On D, we've got 1, 1, 0, and then on G, we've got 0, 1, 1. Now, what's the problem with one of these, with a binary encoded disk? Well, with binary, more than one bit changes at a time. So we're going to get false readings due to incorrect positioning of sensors, because it's quite difficult to put the sensors in, because the angle that we've got of this segment here going past, and then this segment is a whole lot smaller, and this segment is a whole lot smaller, so the positioning is quite difficult. So if we look at something very, very straightforward, going from effectively what would be 1 to 2, something like that, what our might result in is the least significant still staying a 1, while the next least significant bit also goes to a 1 at the same time. So we might actually have, it might go to that, and then go back to that. So we might effectively have 1, 3, 2. Oh, sorry, miss on the pen there. 1, 3, 2. Okay. Right, okay, so the solution then is to use grey code. Use grey code, and the whole idea with grey code is only one bit changes at a time. So only one bit changes at a time, i.e. when you're going from 001 to 011. Okay, so the whole idea is you look to change the least significant. If you can't change that, then you leave it alone and change the next one. So on here, I could have changed the least significant bit. Yes, I could. So I've changed that one and leave the next least significant bit as it is. On this next one, could I make that being a 1? No, because then I would end up with the 1 which I've already had. Okay, so I'm going to leave that alone. If I change that one, no, I'm back to all 0. So I'm going to leave that one as it is, which means then I'm changing the inner ring like so. Can I change the least significant bits? Yes. So if I change the least significant bits, that's that, and the rest of them remain the same. On this one, on this next segment coming round, can I change the least significant bit? No. Okay, so we'll leave that as it is. Can I change the next least significant bit? Yes, I can, because I've not had that code, so I'll go from a 1 to a 0, which means then that inner ring stays as it is. And then finally on this one, can I change the least significant bit? Yes, I can. So that now becomes a 0. That was already 0, so that then is a 1. And then as a final check, coming around to here, I change that to get back to that code there. Righty then. So calculate the resolution of the disk. Well, I'll write the formula down. Resolution equals the degree of the disk. In this case, we've got a 360-degree disk. But you don't always have a 360-degree disk, and it's 2 to the n, where n is the number of bits. So we've got 2 to the 3, so we've got a 45-degree resolution. And we can actually see that there on this disk anyway. If we want an improved disk, so we want a resolution of 3 degrees, obviously, we can obviously swap that round. So we've got 360 degrees divided by 3 degrees gives me what 2 to the n is, which is 120. Now I could use logarithms, but I like the trial and error. So I want a value of n where 2 to the n will be 120 or greater. So therefore, if I make n 7, that would make 2 to the 7 equals 128. So therefore we need 7 bits. Okay, slotted disk. So a slotted disk we can use to measure speed. Something like a fan, where we've got a light beam shining through it. In this case, we've got 200 pulses, and we've got 50 slots in that disk. So we can then see, therefore, if we divide one by the other, we can see that we're going to do 4 rotations in the 30 seconds. So if we want to know in RPM, so revolutions per minute, we need to say, well, okay, so we're going to do double that. So we're going to get 8 RPM, 8 revolutions per minute. So our maximum speed is 20 revolutions. So what would be counted? So if we've got 20 revolutions and we've got 50 slots, therefore 20 times 50 gives me 1000. And finally, a good old resistor value there. So if we've got 5 volts coming out of there, we've got 2.1 volts across our LED. So our resistor value is voltage divided by current. So therefore 5 minus the 2.1 divided by the 20 milliamps going through it gives me a safety resistor value of 145 ohms, and that is it.